Welcome to the PPT. This is Vikas from IARE Data Science section. We are going to discuss about a formal description of inductive air interference using Thévenin's theorem and numerical analysis. The topic is like to discuss about Thévenin's theorem and numerical analysis using that. When we go to the next slide, let's first see about introduction. The introduction is: for years, so-called biotelemetry system monitor virtual functions such as ECG, blood pressure, and so on. For so many years, this is functioning. As the result, several proprietary near-field communications (NFC) standards exist in human and veterinary medicines. When we go to the next point, the aim of our investigation is to replace some of these devices by standardized radio frequency identification (RFID) technology. We want to replace the old ones with the new ones. So this is our aim to do. This PPT presents a new technique to calculate the magnetic field and the needed antenna parameters together with coupling using numerical analysis. Our PPT presents a new technique how to calculate the magnetic field and the needed antenna parameters together with the coupling using numerical analysis. We'll discuss in this PPT about numerical analysis and techniques to calculate magnetic field and antennas, about antennas parameters together. When we go to the next slide, let's wait for the slide. State of the art. What is state of the art? Let's go into that. The loosely coupled transformer model is able to describe all electrical interactions, but to determine the impact distance, theoretical papers often refer to formula description of coupling between two circular shaped antennas. This is about two circular shaped antennas formula description and do not consider the impact of different geometries and the coupling factor, so called asymmetric coupling. We do not consider the impact of different geometries on the coupling factor, so called asymmetric coupling. When we go to the next point, furthermore, the calculations of inductance is linked to separate formulas. If we want to calculate inductance, we require separate formulas without any context to the description of communication or power line. In case of complex geometries like coupled rectangular spiral inductors, no formula exists for calculating inductance analytically. Calculating the inductance analytically. So like very complex geometries like rectangular spiral inductors, we don't have a formula to calculate inductance. So that's why we are developing this paper. So let's go into the paper. So when we go to the next slide, let's see what happens. To overcome this difficulty, like we don't have a formula analytically to calculate complex structures or geometries. To overcome this difficulty, many applications use numerical methods. Like they use numerical methods to determine magnetic field as well as coupling factors or mutual inductance. Like so many publications used determine like formulas. They were using numerical methods to calculate. Typically, stimulations based on finite element methods or the partial element equivalent circuits are used. So these are used, like both methods are more precise than theoretical studies and furthermore are able to consider capacitance as well as the skin effect. Nevertheless, precise numerical analysis has the need for complex electrical equivalent circuits to cover all stimulated effects. When we go to the next slide, let's see what happened. Now, concept and paper organization. In this, all components necessary to provide an inductive power supply, including transmitting and receiving antenna, are replaced according to Thevenin's equivalent by linear two-terminal network with a single voltage source and an impedance in series. This is shown in figure 4. Let's see in the next slide. Let's go to the next point. The transformation is done using equations and based on the well-known loosely coupled transformer shown in figure 3. This figure 3 is also in the next slide. Let's see in the next slide. Now let's move to the next point. All the parameters depending on geometry are calculated via superposition of the interactions of simple wire segments, so-called strands. It's an example. The next figure 1, 2, 3 and 4 will be shown in the next slide. Let's go to next point. Next slide even. See, let's see the figure 1. It's a schematic view of inductive coupled system. There's inductive coupled system diagram. Solid lines, the ones which are in solid lines are antennas. The ones which are in dashed lines are magnetic flux, and which are shown by arrows are voltages, and dotted lines are distance. Figure 1 is about schematic view of inductive coupled system. Solid lines, antennas. Solid lines are antennas, dashed lines are magnetic flux, arrows are voltages, dotted lines are distance. Let's come to the figure 2. Antenna model for calculation derived from figure 1. The figure 2 is derived from figure 1 antenna calculations. Arrows are the standards. Let's go to the figure 3. Equivalent circuit used to derive two terminal networks. The box includes the components of all transformers. The load or second antenna machine is not connected. All variables are introduced in section 4. Let's talk about it later. Here, figure 4 is about equivalent circuits including voltage source. Voltage source V is there, V, and series impedance ZE. The load or secondary antenna machines is not connected. Let's go to the next slide. We have talked about figures in the previous slide. Now let's to derive the model from random geometry of two antennas. The algorithm takes the following 4 steps. There are 4 steps to derive the random geometry of two antennas. The first step goes to be, in the first step, the used antenna geometry, both transmitting and receiving antenna, is split into standards. Circular antennas or curvatures are approximated by the sum of several tiny standards. Now, second point. Ohmic losses are calculated by summation of particular standard resistance. The inductance as well as coupling are calculated via magnetic flux. Now let's go to the third point. Third point. These parameters are together with a model of signal source are used to transform the inductive coupled system into two terminal networks. The following electrical circuit calculations are done by connecting additional electrical components to the terminals of the receiving antenna. Example. Let's take an example. Machine cutting circuit plus load resistor, or simply a load resistor. A fourth point. With the help of resulting current, the magnetic field can be simply calculated and plotted by superposition of every magnetic field generated by every standard according to Biot-Savart's law. Now, electrical mode. This is an electrical mode to transform a magnetic coupled electrical system into two terminal network. A loosely coupled transformer as shown in figure 3 is used. The figure will be shown in the next figure, the next slide. Now let's go to the next point. It is powered by a voltage source Vs, which is connected via matched impedance Zs. The ideal voltage transformation is described via the turns ratio gamma. Now gamma is N1 by N2. Resistor characterizes energy losses and inductance model the magnetic effects. The resistor RC, the so-called iron losses, can be neglected under the conditions that no metal is in between transmitting and receiving antenna. Now let's go to the next point. The inductance are given by the magnetic flux, which can be separated into two parts. Inductance is given by magnetic flux, which can be separated by into two parts. The first part is flux which only flows through one antenna. The second part is the flux which flows through two antennas, both antennas. In this way, the particular antenna inductance can be separated into leakage inductance L sigma 1 or L sigma 2, as well known as magnetic reactance Lm. Lm is K12 L1, L sigma 1 is 1 minus K12 into L2, L sigma 2 is L2 minus K12 by gamma square L1. Gamma is N1 by N2, which we have discussed in the previous slide. The magnetizing reactance is generated by the shared flux in between the primary and secondary winding. Now, the figure 5. Equivalent circuit used to derive two-terminal network after the transformation of primary components and neglecting the iron loss. Previous slide we discussed about iron loss. This is what the circuit is like. This circuit is based on now Vs star is equals to 1 by gamma Vs and X star is equals to 1 by gamma X, gamma square X. The circuit shown is converted into the circuit as shown in figure 5. After Thevenin's theorem, an equivalent voltage V is formed using the open circuit voltage, which is generated by a voltage divider between the transformed magnetizing reactance and the other transformed components from primary side. Now the let's of V. V is equal into Rs by J omega L star 1 plus R star 1 plus Zx. Now let's go to the next point, next slide. For the two terminal networks, the components are from the primary side Vs, Zs, R1, L sigma 1, Lm are transformed to the secondary side. Therefore, ideal transformer is omitted in this one. Now let's go to the next slide. Insertion of 2, 3 into 7 and 8 yields 8. It shows that the equivalent voltage is proportional to the primary coupling factor and inversely proportional to the turns ratio. This is very important point. As expected, the voltage rises with the number of turns on the receiving antenna and falls by increasing the distance between transmitter and receiver. In addition, the voltage strongly depends on matching the primary antenna. Now let's go to the next point, next slide. The equivalent voltage is sufficient to describe communication signals, but for power transformer, it is necessary to model the series impedance. After Thevenin's, the series impedance ZE can be calculated via the short circuit current ISC as follows. ISC is equal to Vs by 1 plus R2 plus J omega L sigma 2 by J omega L hash H1 into Z star Q plus R star 1 plus J omega L star sigma 1 plus R2 plus J omega L2. L sigma 2. The series impedance in the ratio between open circuit voltage current using 8 and 9, the resultant equivalence 10 can be formed. The below equation is formed. In the case of symmetrical coupling, both antennas have the same size but the number of turns may be different. The secondary inductance can be removed as follows. This is the formula for that. How it and we can remove it. Now let's go to the numerical analysis, the main part of this one. In that, let's discuss about theory first. Basic idea of the method is the given random geometry of two antennas can be approximated by a number of standards as and the required values can be calculated by summarizing the individual results. To deploy such a method, physical correlations have been found in which into a series. For example, to determine the ohmic losses R1 and R2, the relation between the resistance R1, R and length L, together with the needed parameters resistivity rho and cross section area A is used follows equals to rho A n into L. The other parameters are related to magnetic field. The H field is calculated according to the Thévenin, which describes the magnetic field strength H in a test pointer. R is generated by constant uniform current I through a coil which with a locus S around its shape. The HR is given in the down formula. Another field dependent quantity, the magnetic flux, given the inductance L1 coupling factor K12 in the context, so we call the is deployed phi is equals to S ds, similar to that in. It can be described as the integral along the locus of coil as follows. The permeability mu describes the influence of the medium. If there is only one medium, example air, it can be considered constant. The electrical current can be ignored for the calculations of inductance and coupling factor. The primary coupling factor is the ratio between flux through both antennas 1 and 2 and the total generated flux 11 by transmitting antennas as follows. The inductance is given by which is derived from definition of induced voltage and inductance. It's there in the down, the formula. Calculation of magnetic field. This is important. How to calculate magnetic field. The integral describes in 13 we split into a number part integral using the sum rule. The down there is formula. After that, an example for rotation around the z-axis specified by the angle between x-axis and stand is shown as follows. It is represented in a matrix RT alpha. In this way, the h function is related to h naught is defined according to given below one. This formula given in the h bar. The function h naught corresponds to the integral of formula. It can be stretched by changing the integral borders and solved in any direction. Hence, the function is set into the origin and oriented along the x-axis, which is given down. For multi-antenna systems, the superposition principle is used in which the resulting field is calculated as sum of all antennas. Using this equation, it is possible to calculate different antenna configurations. Calculation of electrical parameters. To calculate the needed parameters for Thévenin's theorem, equivalent R1, R2, L1, L2 and K1, two steps are necessary. At first the ohmic loss and then the flux related values are computed. The given r1 is given down. The following the lines integral in is n is substituted by auxiliary functions beta as follows. The auxiliary function is calculated by displacing and stretching of an individual line. Integral follows b naught. The given there is formula down. To provide the standard principle, the integral is shown in the split parts. All line integrals are solved with only one function phi, as shown in phi. In below phi sigma of 1 to n phi y bar alpha I L. This is as well as changing of direction is done by multiplying e small y segment s of stand, which is unit vector as follows. The unit vector is given down. To move the start position is changed by constant value. The resulting function is shown as follows. Figure 9. Stirred model used in case study. This is used in case study. It shows a common RFID system. Big solid arrows, the stirreds to calculate vector potentially. Dashed arrows. The ones which are in dashed arrows are used to calculate flux. The ones which are in dashed arrows are used to calculate flux parameter. D is a parameter. It's like to find the distance between two antennas. When two antennas are placed in at a distance D, D is the distance to find between two antennas. Used to calculate L1, L2 and K12 according to equations. L1 is found by N1 square 5 star 11 mu by 4 pi, as well as same as L2 is calculated N2 square 522 star mu by 4 pi. K12 is calculated by 5 star 12 by 5 star 1.